Hello students. Today we'll see in details of binary search tree. We already have introduced what is binary search tree in last week. So now today we'll discuss about in details, and we'll try to see some implementation of binary search tree. We have a time. If we have a time, if we don't have time, then we'll cover in the following class. Okay, so let's try to try to uh, recap everything that we have covered in last week about the binary search tree. So what is the reason of using binary search trees? So this is because we want to search something, you know uh, searching is the basic operations when we try to write any program, when we try to do any operations, because our programs, our applications basically work with several data. So when they work with several data, they basically try to find out those data from different database or different files. So if you don't have any efficient algorithm or process to find data, then probably you need more time to do operations. So that is the motivations that we have a different data structures called binary search tree. So binary search tree provide a way that you can find a data very efficiently, or in a faster way. So these are the motivations, because we have some other data structures like arrays and linked lists. They have some limitations. For example, for searching data in arrays fast, if you know the index, if you don't know the index, then probably you need big and complexity. You need to search everything in an array in our case. But if you want to update something, probably you need some more time, because if you want to delete a data, probably you need to shift a lot of data to cover the empty place. And if you want to insert something in between, some in between in the arrays, then you might need to shift all data to the right side to make a room for that new data. So this is not an efficient thing. So if you talk about the linked list, so linked list has a better way to inserting and deleting, that you don't need to shift anything, but it has a you know it has a limitation, that if you want to search something in a linked list, you might need a longer process, because there is no index. So if you want to search something, you have to visit all nodes in our case to find something. So the idea is to that we want to eliminate these limitations what we had in array and linked list. So we'll try to develop a new data structures, that new data structures will not have these limitations. So BST provide better representations for our data. So we already have discussed what is the basic definitions of BST. BST basically says that it's a binary tree. That means you have at most two children of each node. You can have zero children, you can have one children, you can have two children, but you never have a node never have any more than two children. So, and it also says that the additional condition is that with this binary tree, that all the values in the left subtree should be lower than equal to the root node. So here it's representing less than equal to, but most of the algorithm provide only less than. It's not equal to, because most of the algorithm do not provide duplicate value in this binary search tree, but you might have duplicate value. If you have duplicate value, then you can provide mm, all the values in the left side should be less than equal to the root node, and all the values in the right subtree should be greater than equal to root node. So value in the root node. So this is the basic basic definition of the binary search tree. What you have values, the left subtree always contain less than equal to all the values in the left subtree should be less than equal to the values in the root node, and all the values in the right subtree should be greater than to the greater than the value in the right node. So this is the definition we have seen in our previous class. So this one is the example. You can see that all the values over here are less than equal to this root value, and all the values in the right subtree are greater uh, than root value. So if you consider each node, so for example, if you consider this node, left value has lower than that value. If you consider this node, left value has lower than this node. If you consider this node, right value is greater than this value, there is no left value. If you consider this node, right value is greater than this one. If you consider this node, left value is lower than this one, and right value is greater than this one. If you consider this one, left value is lower than this one, and right value is greater than this one. And if you consider this node, left value is lower than this one. That means each node satisfies the binary search tree conditions. So if all nodes satisfy the binary search conditions, the binary search tree conditions, then you can say that whole tree is a binary search tree. Now, so in a binary search tree, the values are are kept in a ordered. So you can sort the data very efficiently, so easily. So you don't need to sort. You don't need any other process to to sort the data. So the data already sorted. So you can see that the the left so you'll see that how we sorted. We'll see examples. So for examples, so this is an example. Say if you traverse if you traverse the whole whole site, say this is the algorithm how you can sort the print the element in a tree in a v orders. So sort is your method. So if v is null, then it will return. So if if tree is empty, or if you're done with the all nodes, then you are done. This is the base case of your recursive functions, and you have some sorting algorithm. So just try to understand what is the traversing, traversing style. The traversing style is look like is in order style. So you can see that you are visiting late first, then you print the data in between visiting left and right. So it's an in order style. So if you're printing in order style, probably you are sorting data properly. So go to the left side. If you start with the 3, so that is saying that go to the left side, then print the data, then go to the right side. Okay, so you start with the root, go to the left side, go to the left side, go to the left side, and there is no any left, so you print the data 11, then go to the right side 18. So 11 18, then you're done with the 11 18, then you print 21, then you print 31, then you print 33. So 11, 18, 21, 31, 33 is already in ascending order. Then you go to the right side, say you print 60, then you print, you go to the this side, then left side 81, 86, 87, then 90, 94, 96. So if you follow in order fashions, then you can print the ascending order of the data which are already kept in binary search tree. So binary search tree contains data in an order, so you don't need to sort, you don't need any process to sort the data. So the complexity says that, so for printing sorted data, you probably need big O n complexity. So big O n is the number of nodes. So you need to print all the nodes. You need to visit all the nodes. So that's why its complexity is big O n complexity. Now searching is very efficient in binary search tree. We already have seen in our previous week. So how we can search a binary, how we can apply binary search algorithm in a binary search is very easy. For examples, you are looking for 86. So we know that 86 is, you start with the root, you know that 86 is greater than 33, so you should not go to the left side, because all the value in the left side is less than equal to root value, so you go to the right side. So you compare the 86 with the 60, and 86 is greater than 60, so you should not go to the left side and you go to the right side. And you compare the 90, so 86 is lower than 90, so you go to the left side, don't go to the right side. So you go to the left side, you compare the 86 and 86, and you found that data. So how many comparisons you have done? 1, 2, 3, 4. So using only 4 comparison, you found the data. So this is more efficient. So if you have array, with this data, and you are using array to find, you are using array to find some data, probably you might need big O and complexity, but here you don't need big O and complexity. But we will discuss what is the complexity in searching in binary search tree. So this is the process how we do the binary search tree. So this is the algorithm to find by for to do searching in the binary search tree. If v equal to null, then return null. This is our base case, because this is a recursive functions. If tree is empty, or if you're done with the all, if you're done with the process, then you are done. You probably find the data, or probably you not find. So other base case is you already found the data, then this is the base case, then you can you can terminate the recursive process if you already found the data. If you don't found the data, if your target value is less than the value of the root value, then you go to the left side, otherwise you go to the right side. So this is the normal basic algorithm how search process happen in the binary search tree. So the analysis says that search traverse only a path down from the root. So we basically, you can see that we are traversing only one path to find the results. So when we are looking for 86, we traverse this one to this one, this one to this one, this one to this one. If you are trying to find out 94, you will traverse this one, this one, this one, this one. If you are trying to trying to find 18, you will traverse this one. So that means when we try to find any data, we basically traverse only one path. So that start from the root and it ends with the to the our target value, or if we don't find data, then it will end at the leaf of that path. So does not traverse the entire tree. So this is not traversing the entire tree. So we can say that the complexity of searching algorithm is big O h. What is h? H is the height of the tree. So we already know that how to calculate the height. Height is the longest path of a tree. Longest path of a tree. So it could be possible that you are finding a data that is that is that is in the leaf of the longest path. If it is in the leaf of the longest path, then you have to traverse the whole path to find that data, and that path is the longest path, and longest path is the height of the tree. So you can say that the complexity of a searching algorithm in a binary search tree is height of the tree, big O h of the big O h. Now there are some two more basic operations in binary search tree. So how to insert data into binary search tree, how to delete data into binary search tree. So you cannot randomly insert data into binary search tree, because this basically follows some rules and regulations. So that's why you have to follow that how to insert the data. So for example, you are inserting data 25. So you cannot insert 25 at the right side of the 33, because 25 is not they're larger than 32, so you have to go to the left side, so you go that side 25. So you compare the 31, so you cannot insert 31 to 25 at the right side of the 31, so you have to go to the left side, you go to the left side. Okay, so after coming to the 21, you see that 25 is greater than 21, so you cannot go to the left side, you should go to the right side. So when you go to the right side, you see that there is no any tree, so you can insert 25 over here. So 25 should be right child of the 21. So you can see that 25 is right child of the 21. So that basically similar to the searching algorithm. You have to search the position first, appropriate position first. Then after finding the appropriate position, then you can add that new data. So searching appropriate position exactly similar to the searching data that we have seen in our previous examples, in our previous algorithm. So we have seen that search algorithm is big O age complexity. Probably it also the insertion also have a big O age complexity because it's similar to the a searching algorithm. So because in order to insert something, you have to find the appropriate position that you can insert the data. So you can see that insert algorithm, if v is null, this is your recursive case, then it's basically return the whole tree, or your data. It's return the your data. So then you compare, if k is less than your data of the node, then you go to the left side, and when if the left side is null, then you insert data. If left is null is not null, then you call if it is not null, then you call that insert method again. Let me find. Okay, if v is null, then you insert that the new item to the left side. If it's not null, then you call the insert method with the left child. Similar happen in the right child also. If your data is greater than the node of the value of the node, then it go to the right child and do the same things. If right child is null, then it's insert the data. If right child is not null, then it go further right or further further process. So this is the same thing. You have to find the process, you find the appropriate position first, and after finding the appropriate position, then you insert data. So when you find that there is no need to traverse, then you can insert data. So this is the how you can insert data. So similar the searching that we have seen, the traverse a path from root to the inserted node. So you have to since the complexity of big OH. So probably you are inserting. So it could be possible that you are inserting data at the leaf of the longest path. If you are inserting data at the leaf of the longest path, then you have to traverse the whole longest path to reach the leaf of the longest path. That's why is we know that the longest path basically representing height of the tree. So that's why inserting in a BST is height of the tree. Or complexity is big OH complexity. Now, another important operation of BST is deleting. So, deleting is a very complex than inserting. So, inserting is simple. You just need to search the appropriate position, then you can insert the data. But deleting is complicated because you delete anything. You can delete anything. So, when you delete anything, you have to maintain the BST conditions. So when you delete something, and after deleting, if your updated tree violate the BST rules and regulations, then your tree would not be a binary search tree anymore. So that's why you have to think, in a different way. After deleting something, you have to maintain the BST in some additional processing. with a additional process. So a delete can happen in a three different way. So you can delete a child, or you can delete a leaf, which is simplest way things. You can delete a parent which has one child, and it could be possible that you are deleting a parent which has two child. So if the case one you are deleting a, that is simple leaf, then you don't need to do anything. So you just say, for example, so you want to delete 18. Okay, if you want to delete 18, you just make 11 dot right equal to null, because the 18 is the right child of 11. So if 11 dot right equal to null, that means you delete 18. So there is no more link to the 18. So, and it would be treated as a garbage, and it will be removed from the memory. So it's simple. If you are trying to delete in a child that doesn't leave, then you don't need to worry about that. You just make the parent dot right or parent dot left equal to null, then you can easily delete the child. So for example, if you want to delete 81, so you have to do that 86 dot left equal to null, then there will be no link between 86 to 81, and 81 will be deleted. So these things happening over here, we are saying these things. If x is left of the parent child, set parent of x dot left equal to null. So if you want to delete x, then parent of x dot left equal to null if x is left. Otherwise, parent dot x dot right equal to null. So in all things, that basically saying that x is a leaf. If x is the leaf, then you can easily do the process. Now consider you want to delete a node. That node has one child. If that node has one child, then what you need to do, you need to shift you need to shift your data to to the parent place. Say for example, so, you want to delete 11. If you want to delete 11, so what you need to do, you need to shift 18 to the to the 11, to the place of 11, because you have to make a link 21 to 18, because you are deleting 11. So 11 is in between 21 and 18. So what you need to do, so you need to replace 11 by 18. So for example, you want to delete 31. If you want to delete 31, so you have to replace that 31 by 21. Then you can make a link to 33 to 21. That's basically saying that if you want to delete a node with one child, so these all node have one child, so they have all have the same process. If you want to delete 21, or if you want to delete 31, or if you want to delete 11, all will have the same process. So link parent of x to the child of x. So parent of x, so this is x, so 11 is x. You want to delete this one, so parent of x means 21, link to the child of x means 18. So you have to link a 21 to 18. So this is little bit complicated than the previous one, the little thing leaf. So you have to shift over here. Say for examples, you want to delete 60. So if you want to delete 60, then probably you have to make a link 32 to 90. So because this is you have to you have to link 90 to 33, so then you can remove 60. This is another process of deleting if you want to delete a node that is one child. Now the question is that the more complicated thing is that if you want to delete a node that has two children, that is two children. For example, so you want to delete 90. If you want to delete 90, then you have to find out which node should be used to replace 90. In the previous case, there was only one child, so you are fine with the with that. You can take the 90, because you don't need to worry about the other things. You don't need to compare anything, because there is one child to link. But now you are deleting 90. Now you have to link 60 to one of them, 86 or 96. So you have to find out which one should be. which one should be. So, and you need to find out that whether connecting 86 and or 96, the proper connecting 86 or 96 is still maintaining the binary search condition or not. So that's why since this is a complicated, so that's why it's following some algorithm. You have to follow some algorithm, some process to the third delete process. So what is the process? So you can follow one of them process. There is two different process, so you can follow one of them process. So for example, so you are deleting 90, you have to find out the leftmost child of right of x. So if it is an x, so you have to find out the leftmost child of the right of x. So what is the right of x? Right of x is this one, this right subtree of this x, and you have to find the leftmost data of the right of x. Leftmost data is 94. So 94 is the leftmost of this right of x. So you can replace 90 by 94, then you can maintain the BST conditions. Now other way is that, so you can find the rightmost element of the left subtree, rightmost element of the right subtree. So this is x, and rightmost element 8 is 87 of the left subtree. So you can replace 90 by 87, then you can maintain the BST conditions. So this is the things that there is two different way that you can delete a node which has two childrens, then you can maintain the BST conditions. So you follow this one when node has, you know, no, yeah. So you follow this one of the process to maintain the BST conditions. So you have to try with several exercise to clear your concept, to concept clear, to make your concept clear. So this the this you will find several exercise on the textbooks. You will do those things, and or I'll try to give some assignments also, then you can you can understand the process. So now analysis. So traversing a path from root to the deleted node, and sometimes from deleted node to the leftmost child or rightmost child. So this is basically also saying that the complexity is big O h. So the height of the tree is the complexity of the process, deleting process. Probably you want to delete something in the longest path, and you have to find your new data to replace that deleted positions. To the deleted position, probably you need to traverse the whole longest path. So in that case, the complexity of big O h in that case. So far we have seen that insertions, deletion, and search, all three has the big OH complexity. Now, if a tree has, we know that tree has this number of nodes. H can be, height can be n minus 1, or height can be logarithm n plus 1 minus 1. How could be possible? So our tree can be something like that. If our tree is something like that, so 11, 33, 60, 81, 86, yeah, if our tree is something like that, then you can see that the height is the number of n. So big O(n) is the equal to the so n equal to h. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there is n. So you can say that a in height and number of nodes are similar. So we can have similar type of tree, and we can have this kind of tree also, that is a better shape of the tree. So here height is much smaller than the n. So if we have tree something like that, and if you want to delete something and insert something, probably the complexity is big OH, which is actually big ON. So you can say that, so in BST, so insertions, deletion, and searching could be big O(n) if you have had, if h is equal to int. So this is something like that, which is basically similar to our searching and linked list and array. But this is very rare case. We don't have this kind of, BST. We probably have, in average case, we probably have this kind of tree or something, worse than that. But this is also a rare case. So in our case, h is a big one that we have seen, that we just told that BST insert search delete, but probably we can say that big one complexity, that's just like a linked list and array. So far these all details of the binary search tree. In the following slides and our following class we will see the implementation of binary search tree. Thank you very much.